compensation and error checking and so forth, and you end up, it's not all that difficult to process the information anymore through the photodetector. You do move your sample, and you need to be able to move your sample at very, very small distances, and that's typically done with piezoelectric displacement devices, right? Because those can move very, very small distances, sub-angstrom potentially, right? Just by slight variations. And in that case, you're not moving something by atomic distances even. You could move it by subatomic distances just by slight changes in the voltage where you're changing the spacing between the atoms in the piezoelectric material. Okay. There's a number of different phenomena that you can glean from this. You could look at different forces that come in the surface. So you could look at magnetic forces. You could look at coulombic forces. All kinds of different things. You could look at friction. I'm a mechanical engineer, so we tend to care about things like friction. Adhesion, right? So if you want to make a surface that sticks better or worse than something, then what you would do, let's say that I was interested in how well two materials stick together at the atomic level. Well, what I would do is I would make my tip, on my AFM tip, I would put one of my materials, and on the substrate, I would put the second material, and I would study that interaction. Okay? So there's a lot of degrees of freedom that you can do as an experimentalist with atomic force microscopy. All right, moving on, another morphological technique. This is probably, I think, the most common technique that's used certainly in my lab and the ones around me. This is looking at a surface as a visual image that's gleaned from an electron backscattering event. Okay, so this is scanning electron microscopy. Here what you do is you take an electron beam, you have a gun at the top, an electron gun, not the other kind, and then you focus the beam using electron optics. There's some electrostatics, some magnetics that go into that, and then you focus it down to a point, and from that point you look at the backscattered image, and that can give you a picture of the surface. It doesn't give you a color image, right? It's not like an optical microscope. You can colorize these things. I know it's easy in Photoshop nowadays, but it gives you a black and white image, and it can tell you much about the surface structure. For us, in my work, and I think in almost all of the laboratories around the world working on energy materials and nanotechnology, this is a very common screening technique, and the hardware for scanning electron microscopes has become quite common and relatively affordable. So SEM, pure SEM, will give you morphological information, topography, and morphology. Morphology is the surface shape and texture of materials on a surface, and topography is more about the quantitative dimensions of a surface. So they're very much related. EDX, so this is energy dispersive X-ray spectroscopy. Here, this will give you actually elemental analysis. So it goes beyond the surface morphology and gives you some elemental information. It's a little bit more complicated. I won't go through it today, but it's very useful. So usually EDX is something that's added onto an electron microscope. And so we use it. I may have an occasion later this week to show you an example of EDX where we've made some nanostructures, and we did it in a synthetic way that was not highly controlled, and so we wanted to know where the elements ended up. We made basically a soup, and we cooked the soup, and we weren't sure what was left at the end. Well, EDX is a way to give you that kind of information. Here's an example SEM. Again, you know, the raw images are rather boring. This is, again, from one of our papers on rapid synthesis of graphene. This is a graphene surface. It's actually rather thick. You can see some grain structure. It's sitting on a copper substrate. You can see some grains of the graphene. Actually, they're showing through some grains of the copper substrate underneath because the graphene is very thin. But this would be something where you could at least tell yourself, you know, have I grown graphene, and is there some kind of granular structure on the surface? XPS is a functional technique. We use this quite a bit. It's usually somewhat specialized. The equipment is very expensive, but it's extremely useful because it tells you about bonding in the material. Again, it gets back to not just knowing what elements you have, but knowing how they're bonded together. All right, so what happens here is you shoot an X-ray at a surface and you excite the electron enough so that it comes out of the material, and because you knew something about or know something about the electronic states of different bonding arrangements, because when I say a chemical bond in a material, what we're really talking about are the electrons in the bond. And so you have sort of a catalog of bonds of different materials, and usually you know at least what the elements are or what they might be in your material. You have this catalog of bonds, and what you're really doing in XPS is measuring the bond energy. And so you take a spectrum. That spectrum is going to go across a sweep of energy ranges that you can control as the user. And then you say, well, okay, I saw a peak in the energy spectrum of the electrons that I measured coming out, and that peak would correspond to this kind of bond. All right, so that's the general idea. Again, the hardware is rather complicated, but what happens here, and just to kind of give you an idea of what I just said, you have these these electronic states. You know, typically they'd be hybridized in a material, in a solid state material, and you have an electron that comes out. The photoelectron that comes out is going to have a certain energy that you would measure, and then what you have to do is, you know, that energy alone is not enough. You have to adjust that energy that you actually measure. You're going to measure KE, the kinetic energy of the electron that comes out. You adjust that by the photon energy or X-ray energy that came in, and when you make that adjustment, then you would be able to know through subtraction what the bond energy is. So it's a little bit complicated. The direct measurement here is a measurement of kinetic energy. So let's look at that energy analyzer. You have your sample, an X-ray source strikes the surface. Again, we have to use some electron optics, some electron focusing techniques. You have this semicircular entity on top. It's actually semi-spherical. If you see an XPS machine, it will have what looks like the top of a mushroom on it, made out of metal, a metallic mushroom head. And inside of that, you have two plates. You have two plates that guide the electrons. By varying the voltage on the two plates, you can determine what energy of electrons hit the other side. That's your detector on the other side. Now you might say, I wonder if there's enough electrons coming out, because after I've filtered or focused and had a slit for the electrons that came out of my sample, how many could possibly be left at the other side of all of this, right? Especially in a small energy range. Because I'm adjusting the voltage on the bottom and top plates of my analyzer so that only a certain number of those electrons actually reach the detector. That's a very difficult proposition. So what you have to have is a detector that's very sensitive. What kind of detectors are very sensitive? Well, The detector is not a single entity. What really happens is you have an electron multiplier. They call this a channeltron. I don't know why they call it channeltron, but they have an electron multiplier so that when one electron hits the detector, many electrons come out, and that's what you actually detect. Okay? So this is, again, is a fairly complicated device, but it tells you, much about the types of bonds that you have, whether they're covalent or ionic. Again, most of the time in XPS, what you're doing is you're measuring this energy spectrum, and then you're comparing it to some sort of a reference library of energies of different bonds. I'll show you an example here. This is from work that we did again on growing graphene very rapidly. And here you're going to see, again, I told you we grew the graphene on copper, which is very common to do. We kept the copper in this sample, and you'll see that this binding energy curve is given. So the spectrum is given. A lot of times, one of the confusing things about XPS is that you think that the people who do XPS may be dyslexic. I don't know if you know what that is. I'm slightly dyslexic. It means that the numbers go in the wrong direction. Right? It's because it's binding energy. It starts from 0 on the right and then goes up this way. It's because of that. Really, the binding energy is a derived quantity. It's subtracted. So you go through this and you see these very sharp peaks. And so this is a really good thing to look for when you have a sample, let's say with a background material that you know is there. A lot of times it'll be silicon because we do so much in nanotechnology with silicon, but you want to look for the silicon peaks because then you know that your system is working. In fact, you can use those peaks. If you have some kind of drift in your sample, you can actually use those known peaks to calibrate your source, right? That's done routinely by the expert. So I have these copper peaks here at about 900 electron volts of binding energy. And so you know where those are in that catalog that I talked about. In that recipe book of, okay, so copper has a peak, the 2p peaks are here, and you just know that, and you say, okay, that's my reference point. Now then, these other things you're not so sure about because it's what we grew. So you have, in our case, the 1s peak of carbon is known, and we see it there. So we're happy. We see carbon, which is what we grew. If you don't see what you wanted to grow in XPS, then you probably did not grow it, right? It tells you something also about the bonding. In this case, it tells you sometimes what's not there. And that's why I chose this example. Many times in XPS, you would want to know what's not there. Most of the time, when we do carbon-based materials, we don't want oxygen around. Oxygen is sort of a contaminant, right? Well, we have the oxygen 1s peak, and we show that it's essentially non-existent, right? So that's good. That's good. Another technique, BET, named after its founders. So BET, what you should think about with this technique, pretty simple. You want to measure the surface area of your material, okay? And it doesn't give you some kind of absolute surface area. It's a surface area relative to the adsorption of a species onto the surface. Because true surface area, what does it really mean? If you told me that you had some multi-layer graphene, and you know that the graphene itself is not bonded, it's only weakly bonded to the different layers in the C stack. Well, should you count the bottom, the in-between parts as surface area or not? I mean, we know that things like lithium ions go in there, so they can access that area. Should we count it or not? So that's the point. I mean, surface area is difficult to define. It's kind of like on our cartography, right? If you make a map of a coastline and you say, what is the length of the coast? You can't really definitively answer that question because it depends on how much granularity you want to get into. Are you going to measure the length of every rock on the coast? Or are you going to do it at some level, you know, at a satellite level or something, right? So that's an important distinction. So this is a particular technique, and what it's useful for is not necessarily giving you an exact number of the surface area for whatever function you're going after, but it can give you relative surface area of one thing versus the other, so that in the functional manifestation, you should know if it's going to be better or worse than whatever your control is. So the BET technique essentially works on the on adsorption. So at the adsorption of typically nitrogen. So you cool this system down to cryogenic temperatures, and you measure the adsorption processes. You measure basically the pressure in your chamber as you're cooling it down, or you're pumping it down, and you'll know how much material, how much nitrogen you put in, and how much pressure you should have if, for example, it did not adsorb on a surface, because the adsorbed species does not contribute to pressure. So that's the general idea. So that's where this adsorption isotherm comes from. I'm showing you the theory here. I mean, essentially what you're doing is you are on the left side of the top equation, you have a series of